Okay, that's good.
Okay, so thank you. So now we have Swee Hong Chan, who will talk about some log-concave inequalities for posets or a combinatorial atlas even. Okay, please.
Yes, thank you very much for the introduction. And first, I would like to thank the organizers for organizing this conference during this very difficult time. And also, I would like to thank all of the participants for coming also during this difficult time. And the main character for today's talk is the log-concave inequalities. And here is how it's defined. So let's say that we have a sequence A1, A2, A3 up to AN. And let's just say that all of these numbers are positive real numbers, just to make things simpler. And we say that this sequence is log-concave if for any k between 1 to n minus 1, the square of the kth number, so this number here, is greater or equal to the product of the k plus 1 number and k minus 1 number. So for example, this sequence down here below is a log-concave sequence. And one way to check it is that, for example, if I take the number 9 here, 9 squared is 81. 81 is greater than 4 times 15, which is 60. And you can do the same for the rest of the sequence, and all of these inequalities will stay true. So this sequence is log-concave. And one reason why log-concave inequality is useful or important is because, in particular, log-concavity implies unimodality. So this means that the sequence will first increases up to a certain point at this top, decreases afterwards until it disappears. Just like how we hope that COVID numbers would have been in an ideal world. Of course, the COVID number is not unimodal, but anyway. Okay. So the quintessential example of the log-concave sequence is the binomial coefficients. Here, n is fixed and k is changing from 0, 1 up to n. And ak, so the number in your sequence, is the binomial coefficient n choose k. And for this, so this sequence we know is log-concave because, well, we can just do direct computation. If we compute this ratio, ak squared divided by ak plus 1 times ak minus 1, this thing is equal, after some calculation, to 1 plus 1 over k times 1 plus 1 over n minus k. And because our k is between 0 and n, this number is always greater than 1. Okay. And just a little bit of spoiler here, but in the few couple of slides, these numbers 1 plus 1 over k times 1 plus 1 over n minus k will appear again. So it might be a good idea to keep them at the back of our mind. Okay. So the second example for log-concavity comes from permutation, where ak here is a number of permutations of n elements with exactly k inversions, where inversion of a permutation is a pair of I and j, such that I is less than j, but pi I is greater than pi j. Okay. And this sequence is log-concave, and unfortunately, or maybe fortunately, we cannot actually use direct computation anymore, because there's simply no, as far as I know, there's no closed form formula for AK. Instead, what people usually do is that they first write a generating function for this sequence. This is also or the former power series to fix with this conference website. And when you look at this former power series, you realize that, oh, what a coincidence! This power series is a product of polynomials, and each of these polynomial, the coefficients, form a log-concave sequence. And it turns out that this property of coefficients forming a log-concave sequence is preserved under product of polynomials. And that is how we know that the original sequence is log-concave. Up till here, are there any questions about definition of log-concavity? Does everybody think that log-concavity is a friend? Okay, I see no questions, so I presume everything is good. So let me continue. So in general, if somebody hand you an arbitrary sequence, there's no reason to expect that this sequence will be unimodal, let alone log-concave. So that's why if you somehow have a combinatorial sequence and you keep seeing that it is log-concave, then usually the log-concavity there is there for a reason. For the binomial coefficient, let's say that is by direct computation. For the permutations, we see that it's there because log-concavity is preserved under polynomial products. And today, our goal is to discover yet another reason for log-concavity. And this time, this is the reason why we see so many log-concavity for matroids. Okay? That is our goal for today. So I believe that many of you already know a matroid, but let us just do a quick review so that we all have the same notation, have the same understanding. So a matroid is an abstract set system. It consists of two inputs. The first one is the ground set, which is denoted by X. And for today's talk, we just assume that X is a finite set. The second input is I. This is the independent sets. This is a collection of subsets of the ground set. And they need to satisfy two properties. The properties, I will explain in the next slide. But before that, let us just look at two examples, just to make sure that we have a concrete example in our mind. Okay, so that this thing is not very abstract. The first one is called the graphical matroid, where the ground set X, this is simply the set of edges of a graph G, of a given graph G. So, and G here is a finite graph. And independent set, a set is independent simply if it's a set of edges such that they form a forest in the graph. So there's no cycle. So that is one example. The second example is called the realizable matroid, where the ground set is any finite set of vectors over a field F. The field F here can be finite, can be infinite. And in fact, soon we will see some examples with a finite field. And the independent set here is, pardon the pun, is the set of vectors that are all linearly independent to each other. In fact, this is actually the reason why this thing is called independent set in the first place. Okay. And so here is two conditions that that independent sets need to satisfy. The first one is called the hereditary property. So this says that if you have two subsets, S and T, and one of them is contained in the other one, okay, and the larger set, let's say T, is independent, then the smaller set is also independent. For example, this collection of edges has two edges. They don't have forests. They don't have cycles. So this is a forest. Now, if I delete any one of the edges, let's say I delete these blue edges, the resulting set, which is called S, is again independent. It's again a forest, right? Because when you delete the edges, you do not. If you don't have cycles in the beginning, you will never form a cycle at the end. Okay. The second property is called the exchange property. This says that suppose that you have two independent sets, and one is smaller than the other. For example, in this, the set S here, the one with red edges, has one edges. The set T has two blue edges. So one is less than two. So S has less element than T. In this situation, you can always find an element from the larger set, which is this there's these blue edges. You can find one of the blue edges, let's say these blue edges, move it to the smaller set, and the resulting set is again independent. It's again a forest. That is what is called the exchange property. So these two properties are arguably, you can say that it's quite abstract, but it turns out that these two properties are sufficient to get log-concavity for matroid. In fact, in one of our sequel work, we showed that in some sense, these two properties are also necessary if you want to get log-concavity for matroid. Okay. In any case, let me go to any questions so far about the definition of matroids? No questions, so let me continue. Okay, so there are many conjectures about log-concavity for matroid, but today let me focus only on one of them, the Mason's conjecture. So 50 years ago, Mason looked at this number ik, where he said that, oh, let ik be the number of independent sets of size k. In the case of graph, this is the number of forests with exactly k edges. And Mason computed many examples, and he believes that, seems like this sequence I1, I2, I3 up to In is log concave. But now, Mason is a very ambitious person. He thinks that, okay, we cannot prove that this is log concave. But you know what? Let us go for something even bigger first. How about if I add a constant 1 plus 1 over k into this equation? Maybe this is still true. In fact, why stop there? Let us get even more ambitious. Let us add another even one more constant, 1 plus 1 over n minus k, into the right side. And this last inequality is known as the strongest form of the Mason's conjecture. And at this point, some of you might have questioned, but maybe you're just too shy to ask it, is that, Swee Hong, why is it that Mason chooses his constant 1 plus 1 over k times 1 plus 1 over n minus k? What is so special about this constant? Well, this is because many of you might still remember that this number is the ratio of binomial coefficients. So this means that even after you rescale this number ik by this binomial coefficient, then this sequence is still log concave. And notice that by rescaling this by binomial coefficient, this number here now has a probabilistic meaning. That this number is a probability that if you get a random subset of size k, that this subset is actually independent. Okay. And the reason why Mason believed that this conjecture might be true is that because he makes the following observation. Okay, suppose that all subset of our matroid is such that suppose that my matroid is such that every subset with k plus 1 element is independent. Then in that situation, all these three numbers are actually equal to 1, and then you achieve equality. So this means that if this conjecture is true, which we now know is true, then that means that this inequality is tight, that there is nothing we can do to improve. Well, that's actually not the case. So actually, at the end of this talk, we'll show that there's actually a way to slightly improve this inequality. But before I do that, but before we go through that, are there any questions? Okay. Feel free to ask questions now. I think it's a good point to ask questions. Okay. If there are no questions, then let me go to the very brief history of the Mason's conjecture. How we solve the Mason conjecture as a humanity. So the first big breakthrough was made in 2015. So the 2018 here is the journal publication date by Adipratito, He, and Katz, where they show that yes, this sequence is log concave, and they do it in a very beautiful way by using ideas from algebraic geometry called Hodge theory, and they convert it so that it can be applied to the matroid. Okay. This idea was pushed further in the work by He, Schroeter, and Wang in 2018, where they proved the second Mason's conjecture. And the idea here is that rather than working directly with this number ik's, they work with this other object that's called the correlation inequality and apply the Hodge theory. And at the end of the day, after the dust settles down, this constant 1 plus 1 over k magically falls out of the calculation. Okay. And finally, in 2018, 2020 is again the publication date. It was shown independently by Anari, Liu, Oves, Garan, and Vincent. And I think in particular, Cynthia will I presume we'll talk about this more tomorrow. And also by Brándën-Huh, where they show that, yes, the strongest form of the Mason conjecture is also true. And the way they do this is a bit different than the previous two. For this one, they instead develop a new theory of polynomials, where the Anari's group called it strong log-concave polynomials, while Brándën-Huh's group called it the Lagrangian polynomials. In particular, these three works were cited by the International Mathematical Union as part of the reason to award the Fields Medal just 2 weeks ago to Brándën-Huh. Okay. And just last year, this work was pushed a little bit further by Murai, Nagoko, and Yazawa, where they show that the equality can occur in this Mason's tree if and only if every subset with k plus 1 elements are independent. So notice that the if condition has already been known by Mason since 50 years ago. But it's only now that the only if condition is known, that we now know that these are the only equality cases. For all other cases, this inequality is tight. So this is a very short, very simplified history of the Mason's conjecture. Of course, there are still many other amazing works by many other amazing authors. Some of them are actually in the audience today. And that's why I sincerely apologize that I cannot cover all of them in this talk. And before I proceed further, are there any questions? Okay, if there are no questions, then let me continue. So, okay, in fact, let me go back a little bit to the Mason 1 and Mason 3. And I want to look at the evolution of ideas in the proof of Mason's conjecture. So we see that for Mason 1 and Mason 2, we, as a humanity, uses the ideas from algebraic geometry to solve problems in combinatorics. This is a very good idea, of course. You know, algebraic geometry is very beautiful, very useful. But they can also be a little bit rigid. And that is why we see that in Mason 3, rather than using Hodge theory, instead a polynomial theory was introduced to make things a little bit more flexible so that it can prove a little bit more. And today, our goal, our philosophy, is to push this philosophy, to push this idea as far as possible. We want to develop a new tool that is as combinatorial, as simple as possible, so that it can be more flexible, can prove a little bit more. And the result of doing that is this new method that we call the combinatorial atlas, where this method can be used to prove log-concave inequalities. And by using this method, we managed to reprove log-concave inequalities that is known for Matroids, morphism of Matroids, and Stanis-Poisson inequality. And in all these three cases, we actually refine them. We actually prove a stronger form of the inequality. And in other topics, such as the discrete polymatroids, Poisson antimatroids, Brándën gradoids, and interval gradoids, we prove completely new log-concave inequality. Okay. Not only that, this method also comes with a built-in tool to systematically find out the if and only if conditions for equality. So this is very useful because the equality conditions are usually used as a benchmark to show that we have a have a better understanding on the combinatorial structure. Okay. And of course, there are in this list of 7 things. There's no way I can cover all of them. So I hope everybody can forgive me for today if I only cover for the first one. Okay. But before I do that, are there any questions about what we want to do? Is everything clear so far? Okay. Okay, if that is happy, then let me continue. So let me today only show our application for the Matroid to show you how we refine the inequality to something stronger. And unfortunately, the refinement for the general case of my all Matroid is a little bit complicated to state. So let me do a warm-up case first for the case of graph. And in this case, let G be a simple connected graph and let K be the number of vertices minus 2. In this case, we can improve the Mason tree from the constant 1 plus 1 over n minus k to this new constant of 3 over 2. And not only that, we can also derive the equality cases where we know that equality occurs if and only if that G is a cycle graph. So that means it's a triangle, a square, a pentagon, a hexagon, and so on. And I claim that this new inequality is numerically better than Mason tree, because we can show that this constant 3 over 2 is always greater than or equal to 1 plus 1 over n minus k. Not only that, I also claim that this inequality is asymptotically stronger. in the following sense. So now suppose that you take the number of edges of number of vertices, suppose that this number goes to infinity. So in the language of algebraic geometry, this means that I take the genus of the graph, the genus of the manifold to infinity. In this scenario, our inequality gives 3/2 as a lower bound for this ratio, where the Mason tree can only give 1 as a lower bound. This is what I mean by that the bound is better numerically and asymptotically. Okay. Okay, if everybody is happy with this with the case for graph, let me now show you our first main result, which is our refinement for all Matroids, not just for graphs. And our refinement is as follows. In Mason tree, we replace the constant n minus k with a new constant that we call the parallel number, and this number depends on 2 parameters. The first one is that it of course depends on k, and the second one is that it depends on the combinatorial data of the matroid. Okay. And I will define this in the next slide. What is this parallel number? But before that, let me just show you some examples, just so that we have an idea what is this parallel number. First, suppose that you have no combinatorial information at all. You don't know anything about the matroid. You just know that it is a matroid. Then the best we can do is the same as what Mason has done. What Mason has predicted, that n minus k is the best we can say. However, if we just know a little bit about matroid, let's say that I know that this matroid is graphical matroid. Then in this case, we can get the improvement to 3/2 that we saw in the previous slides. And this improvement depends on your matroid. Sometimes it's a big improvement, sometimes it's a small improvement. For example, if you look at realizable matroids over a finite field FQ, then the constant parallel number becomes this constant over here. The exact formula is not very important. The important thing here is that as Q goes to infinity, this number roughly converges to 1 + 1 over n minus k. So this means that this is not a big improvement compared to the original mission. However, in some other scenario, such as for the Steiner system matroid, which let me not define just to save time. In this case, this constant asymptotically actually goes to infinity when you take n and k goes to infinity. So for this particular family of matroid, our improvement is actually very big. But regardless, whether the improvement is big or small, I claim that this is always an improvement, because we can show that this parallel number is always bounded from above by this n minus k + 1. Okay, and therefore this is the improvement. Up till here, are there any questions, except for the definition of the parallel number?
Yes, there is questions. Do you hear me?
Yes, I can hear you. Please feel free to ask the question.
Can you go back to the very first statement of the improvement?
Yes.
Because when you say that k is equal to the number of vertices minus 2.
This one, yes.
So what I don't understand here is the k the same as the index of the independent set?
Yes, this is the same as the index of independent set. And that's actually a very good question, because we actually have the other improvement also for other values of k. It's just that the number is not as nice as not as easy to write as 3/2. So that's why for this one we only put for this number. Yes.
Yeah, but that means that you don't have a family of inequalities in that case, right?
So this is so in this case it's for graphical matroid for any graph, and when the value of k is number of vertices minus 2. For other value of k, we have other numbers for this 3/2.
Okay.
Yes. Just that I just choose this one because it's the easiest one to write. Yes. Thank you for the good question.
So try to finish in 2 minutes now, Swee.
Okay. In this situation, let me just skip the definition of parallel number, and let me show you the second main result, which is the equality cases, right? Because that's what I promised, that we can do equality cases. And So unlike for the Mason tree, where the equality case is basically one sentence, here we have a much bigger diversity when it comes to equality cases, because we just as can be seen from this slide. So, for example, when the parallel number is the largest possible, then the equality cases is the one that the Mason has predicted, which is when every k plus one subset is dependent. On the other hand, when your parallel number is the smallest possible, then we also have equality cases that we have seen from our previous examples, which is for the graphical matroid when the graph G is a cycle. Somewhere in between, when the parallel number is between these 3 and n minus k plus 1, we have the equality cases for the realizable matroids when the matroid contains every vector of dimension n. And there's also another equality cases for the Steiner system matroid, but let me not talk about them to save time. But the takeaway of this slide is the fact that unlike in the previous case, unlike in the Mason tree, here we have many more equality cases. And all of them, at least from the first glance, look very different. However, I claim that despite all of this difference, despite all of this diversity, we can actually unify them. We can actually explain them in one sentence. Okay, one sentence to rule them all, one sentence to unify them, which is our second main result, the if and only if conditions for equality. And of course, even if you look at this directly, it might look a little bit complicated. But I like to think about this in terms of the isoparametric inequality, which is the inequality in geometry, which says that if you have Euclidean object where the volume is fixed, then the surface area is maximized by the Euclidean ball, which is the Euclidean object such that which is at the Euclidean object that is as symmetric as possible. That when you look at all angles, it all look the same. And it turns out that to say something is as symmetric as possible for the for matroid is the same as saying that first, if you basically this description that if you contract the matroid by any independent set of size k minus 1, all of this contracted matroid has the same number of parallel classes. This thing I have not defined, but it's just you can think of this as the codimension 1 faces of the matroid. And the conditions say that all of the codimension 1 faces are the same. And the second one, which is basically saying that all codimension 2 faces are the same. And it turns out that these two conditions on the codimension face and codimension 2 faces are the equality conditions. That once it's achieved, this is that you actually achieve equality. Okay. And let me conclude today by just mentioning that for today I only mentioned the result for matroid, but our method actually is actually a very general method. It can be in our paper we actually use the same method to prove new like 7 new actually maybe like 14 inequalities for 7 different topics, which I list over here. And we stopped at this 7 because at some point we realized that if we keep going, the paper will become 200 pages, not 70 pages. That's why we stopped there. And actually, even after that, we realized that even 71 pages paper is a bit scary. That's why after that, we wrote another paper, which is the expository version of the paper, that is 28 pages. The tools there is a little bit weaker, but still enough to prove Mason tree. It's not enough to prove the refined inequality. But but because of this, the proof also becomes much more simpler and become much easier to understand. So my suggestion is that if you want to start reading this topic, I would suggest to read the 28 pages paper first. And if you are still if you want to learn more, go for the 71 pages paper.
Okay, thank you, Swee Hong Chan, for your talk. So do we have some question for Swee Hong Chan?
Hi, I'm curious how your method compares to the like combinatorial Hodge theory method. Is it similar? Is it completely different? Are there situations where the Hodge theory one is stronger? I just am curious about that.
That's a good question. So the question is about the comparison between the Hodge theory and our method. And as far as I know, they are pretty different. So there's of course some similarities. In particular, we both actually use the fact that we are use this thing that is called the hyperbolic inequality. So that is the underlying theme. But many, I think that's as far, I think in terms of similarity, that's as far as it goes. So other things are actually pretty different.
More questions?
So is it then that you merge the ideas of Hodge theory and Lorentzian polynomials?
That is a good question. So I would say that for us actually we do things from the other direction. So the Lorentzian polynomial and Hodge theory, I would say that both of them comes from the Hodge theory. Well, our direction will actually come from the Alexandrov-Funchal inequality from geometry. So our inspiration is this. So Alexandrov-Funchal inequality is proved by Alexandrov in 1930s, but there's a recent proof by Yair, the Sempel and Van Hendel that give a more linear algebraic interpretation, and that is actually their work is I would say that we are inspired more from that direction. And in particular, because of doing that, one thing that can be achieved from this that I don't know if can be done by the Lorentzian polynomial, is that it allows us to do things on directed version of many of these results. That is actually why we can achieve things on interval gradoids, because in a way gradoid you can think of it as the directed version of Matroid or directed version generalization.
Okay, thank you. Let's thank Swee Hong Chan again.